Hi everyone. Today we're going to start the next section for Module 12A, and this is going to be based out of Steck, beginning of Chapter 16, 16.1, which is going to be on digital to analog conversion. So far what we've done is the first 7 weeks of the class, you did all analog electronics, meaning you're dealing with all these sines and cosine waves at different frequencies, combine them together, and you amplify them, you filter them, you can modulate them, right? Um, and then the latter week, around 8 till, well, the one before this, 11, right? We deal with the digital part where where we figure out how to record information on binary numbers, right? And how does a device, an electronics, like just a computer or something on the breadboard or your FPGA, right? Using logic gates, how you actually process data, store data. Now we have to convert them between back and forth, and then the chapter starts with digital to analog conversion. So, a little example picture here is like, let's say you want to record some sound, like such as what I'm doing on the microphone here, right? The There's an ADC, meaning an analog digital converter, that converts it to digital binary numbers, right? And then stores it on my computer. I upload it to YouTube, but then now this data is on YouTube, right? Um, how when you download this video, right? How does that sound come out of your speaker? The way that happen is using a digital to analog converter. The sound wave that's being stored as ones and zeros, right? They have to be converted to some sort of actual physical sines and cosine waves of different frequencies in order for the sound to come out on your speaker. And then you can hear what I'm jabbering about right now. So let's start off a little bit just the basic of what we need to think about when we're doing both analog to digital conversion and digital to analog conversion. Actually, it's important for both. Okay, and this is the timing resolution. So, and this is known as the sampling rate, meaning the sampling rate is given by, well, how much time do you wait before sampling your each of the waves. So this is easiest if I just had like a little cosine wave here. So notice this is just something I drew on Desmo, right? This is a 10 hertz wave. So going from each period should be 0.1 seconds, 100 milliseconds. Okay. So let's say I have a sampling rate of 1 second. I look at this once per second, right? So if I look at it here at the beginning, right, it'll be like 10 seconds later. I'll look at it later. So you have no idea what the wave actually looks like, right? You don't know what the frequency is. You don't even know, probably don't even know what the amplitude is. So we want to sample, meaning, do the conversion of this wave from either digital to analog or analog to digital, more often than that. Okay. So let's say okay, instead of sampling once per second, right, I sample every 10th of a second. So I'm going to actually start off at a different point here. So let's say I start sampling this point, right? A 10th of a second later is actually one full period later. So that's actually also not very useful, right? Because it will look like you actually have a straight line, right? And then the amplitude, depending on where you sample, actually, you think it's an an offset of a different amount based on where you're sampling. And this is not a good, you know, um, sampling rate. What you want at least, okay, is to maybe sample the wave at least twice per period. So let's say, I'm going to do this in green. So I do this in the beginning here, maybe do a very similar point, right? This green here. Okay, half a period later, right, it's around here, right? And then another half a period later, it's going to be around here, right? Now at least I tell, okay, it's something that's going down, something that's going up, up and down. I may not get the amplitude exactly right, right? But then the frequency is pretty accurate already at this point, right? Because these, if I'm just connecting these points as triangles, at least I know the frequency, how often is it going up and down, right? I may be getting the amplitude slightly wrong, okay? And this is how you can quantify how good your analog to digital conversion or your digital to analog digital to analog conversion is doing. Okay. So, I mean, in reality, you probably want to do at least one more point between these. So maybe like 4 per cycle. But this 2 per cycle number is the minimum. Okay, it's actually known as the Nyquist frequency, which is what we did on the green at the beginning, where the Nyquist frequency is basically whatever your sampling rate is, okay, divide that by 2, okay, and that'll tell you the frequency of the wave that you're trying to do the conversion on at minimum. You cannot do anything less than that. You notice that if I do just, if the frequency of my sampling rate and my frequency is exactly the same, right, I just get 1 point per period and I get the same point over and over again. It looks like a straight line from this blue example here, where if I move to the green, right, let's trace the other extra points, right, at least I know what the frequency is, right? I may not get the amplitude exactly right, okay, but of course, if you do 4, then you actually get a much better um, fit on what the wave is actually doing. Okay, so that's sort of a good thing to know for both analog to digital conversion and digital to analog conversion. So you need to sample enough of the wave so that you kind of get the shape. Okay, and this is the minimum, not the usual. Usually I would actually, go with at least like 5, make this denominator at least 5. And that way you're kind of sampling multiple points on the same wave. So how do we actually do it? You already kind of seen this before, but now it's going to be applied to digital to analog conversion. And this course is going to involve an amplifier. Whenever you deal with analog electronics, you're going to deal with a op amp. Okay. So this little circuit is called a DAC circuit, where along the left here, you have different digital values. So these digital values are going to be, for TTL, it's going to be 0 to 5 volts. So, depending if the input is 1 or 0, you're going to have 1 or 0 to 5 volt here. So this is the digital side of your system. Okay. And then you have these switches, right, to basically tell it, well, is it high? Is it low? Is it 1? Is it 1 or is it 0? And these switches, right, are usually done using some transistor that will either make the connection or not the connection. Okay. So this will be pretty simple. We've already seen those. Okay. And what happened is that, well, if let's say A0 is connected, right, so that means this is at 5 volts. Okay. Then current will run through this first resistor. Okay, go through here and go through RF, right, and then you get an output. And remember, by just looking at that part, right, this is basically an inverting amplifier. So remember inverting amplifier before, so we have some R in, and then you have your amplifier, you put in the negative, you tie the other side to ground, and you have this RF, right, this is V out, this is V in, right, and then the relationship between V out and V in is negative RF over Rn Vn, right? So basically, whatever the ratio of RF over R is, right, you will get an amplification on that. Okay, so V out is going to if A0 equals to on, right, equals to 1, digital 1. Okay, then the V out will be negative RF over R, right? Well, that's Rn. Okay, and then whatever Vref is actually in this case, right? Because that's the reference voltage we're connecting to. But let's say, right, if A1 is 1 instead. So instead of going through R, right, A1 actually passes through R over 2. So V out would actually be equal to negative RF over R over 2 V ref. Erase that. Right. Well, if this is in the denominator, of course, then that will just go to the numerator. Right. So I'm going to see what you notice here. Right. Notice that this and this, the amplification is different by a factor of 2. So if this was the zeros bit, this will be, sorry, the 0 and 1 bit, well, 2 to the 0 bit, this is 2 to the 1 bit, 2 to the 2 bit, 2 to the 4 bit, right? So this has a value of 1 and 0. This will have value in 2 and 0, right? You notice that the values that you have, if the digital bit is 1, right, it doubles, okay? And you're going to see that, oh, if you go to the next level, then you get 4 times, and 4 times, and 8 times, okay? So the general formula for the digital to analog output, meaning you have an analog output, a digital input. This is in, right? The analog is the output, right? Right. In general, you're going to get negative of whatever those digital values, A0, A1, A2, A3, 4, 5, 6, 7, 8, and on and on and on like that. But each time you go to the next bit, you get double the amplification. Okay. So therefore, right, your output is actually proportional to whatever your digital inputs are, right? Right. Multiplied by whatever reference voltage is, and also the feedback resistor resistance divided by your input resistor. Okay. So this is pretty neat, right? It's pretty simple. And you would think, well, that's the way we should do it, right? The problem is on this particular circuit, I'm going to highlight things in blue. Okay. You're going to need very, very precise resistors. Okay. Because, right, if your smallest resistor, right, this is only going up to R over 8, right? That's for 4-bit conversion. If you need to do a 64-bit conversion, you're going to have to go up to a resistor that's 1 over 128. Sorry, R over 128 of whatever your largest value is. So I think I gave a pretty bad example here. But let's say, right, your R, the one that's at the bottom here, right? Let's, pick something that's decent in size, right? 12.8 kilo ohm, okay? The R over 128, which is going to do the conversion for you for the 64-bit, right? That's going to have to be a 100 ohm resistor, right? And maybe this will give you a plus minus, 1% if you buy some expensive ones, right? And then, but you also have to buy the plus or minus 1% on the 10 ohm, which are very, very difficult. Like the lower the resistors, the larger the uncertainty in percentage, because plus or minus 1 ohm here, plus or minus 1% here, is plus or minus 1 ohm, right? Where here, the 12.8K plus or minus 1% is actually plus or minus 100 ohm, right? Right, 128 ohm, okay? Which is much easier to deal with. Plus, instead of controlling your resistance down to 1 ohm, okay? So that's the drawback of the DAC, where you're just doing this direct conversion. Fortunately, there's a way around this, and this is the R to R ladder, okay? So R and then 2R somehow, okay? The R to R ladder, this form like this, you're gonna need like twice as many resistors, but the cool thing is that they are all gonna be just 3 different types of resistor you need. You need your RF, you need your regular Rs, and you need something that doubles that. Because all of these are the same, right? So you're just matching all these resistors, and the difference in the resistance between on the input side is only by a factor of 2 as opposed to a factor of 128 when you need to do 100 when you need to do a 64-bit conversion. Okay. Okay. So how do we make this? How does this work? Right. Let's erase all this stuff. What we do is the way you figure this out is you just start off with the bottom of the ladder, the bottom rung of the ladder. I think that's what it's called. Let's do that in blue. Let's analyze what this bottom rung is doing. Okay. Now we're going to go back to Thevenin's equivalent, so I'm not going to rederive all this for you. But, right, you have 2R here as resistors, right? You're just copying those down. And let's say, you connected that switch. So basically, the input here is whatever V0 is, okay? Sorry, whatever A naught, which is the bit either 1 or 0, times the reference voltage, for example, 5 volts, for example, okay? Right, what happened here is then, right, you have a voltage divider, right? The Thevenin's equivalent of that is basically half the input voltage, right? Whatever this is, right? On connected to a single resistor, which is a regular R, right? Remember this voltage divider Thevenin equivalent? It cuts the input impedance. Sorry, this will be the output impedance of this particular circuit by half. Okay, so that's what that's equivalent is, right? And now what we can do is we can attach that to the bottom of the ladder. I'm going to draw the ladder again just for practice, right? But I'm not going to draw the last part, right? You have this 2R here, then you have a 2R here, right? It's going to be an optional switch. I'm not very good at drawing that part. 2R here, and then you have a ladder of just regular R going straight down. Okay, but we're going to replace this last part, right, with this Thevenin's equivalent, and that goes into the inverting input. You have this ground thing, and then you have your feedback resistor, and you get your V out here. So what I'm going to do is, so this is R, 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 right? Sound like a pirate, right? Since this is equivalent to this, what I'm going to do is I'm going to do this, right? R, V naught over 2, and this is still R because the Thevenin's equivalent, the Thevenin's resistance there, right? It's just regular R because of the 2 R's. Well, the cool thing is that, well, look at this. This is 2 resistors in series. So I can just replace that part, right, with a 2R again, right, with V naught over 2 at the end of it. Okay, and now, right, we have another ladder, another rung of the ladder. I'm trying to exclude that part. Trying to exclude this resistor here, right? So this is once again an R2, 2R, 2R as a voltage divider once again, okay? And what happened is that, well, what this is going to do, so we have V1, V2, V3 here. So the equivalent of this will be basically what V1 is divided by 2, but then V0 is started off as V over 2, but then you're going to have another factor of 2 there. So it's going to be V over 4 when you do this Thevenin's equivalent again, right? Okay. And then that gets connected to another resistor that's right beneath here. That's going to be another R resistor. And then you can see how this kind of chains up to the top of the ladder. Okay. Right. So what happened is that as you climb up the ladder, the Thevenin's voltage of the rung below it gets divided by half. Well, all the rungs below it gets divided by half. Okay. So whatever V out is, the bottom rung, okay, gets an amplification of whatever the A0 value. If it's 1, if it's 0, then you get nothing there, right? So this is going to be the the 4-bit version of it, where the bottom rung gets divided by 16. This is a mistake. Yeah, the second rung gets divided by 8 because you go up 3 times. And then the second rung gets divided by 4, and then the top rung only gets divided by 2. And then so you can pick your RF over R, whatever that is, right? Times your reference voltage in order to figure out, what the dynamic range of your analog output is in order to get the analog value that you want out of your 4-bit conversion, your 8-bit conversion, your 16-bit, or whatever how many bits you want to do. Okay. All right. So that's how you do digital to analog conversions. And we're actually going to use this once again when we go the other way next week with analog to digital conversion. Okay. So that's what the book covers. What we're going to actually do in the lab is we're going to do, you're going to do a small version of this, but on the FPGA, what we're going to do is actually we're going to do something a little fancier called pulse width modulation. And this is a method for converting your digital data into analog. Okay. So this pulse width modulation is actually used by your computer, your phone. These things used to be called MP3 players that only plays music. We don't have that anymore. But this is how a lot of digital sound gets converted from their digital form into analog so that it can be played on a speaker or some sort of sound device that you're using. Okay, to figure out how this works, we're going to go back to thinking about how your function generator, when you push the square wave button, it actually gives you an option to change this thing called a duty cycle. The duty cycle, I think we talked about it a little bit, but we're going to review it right now. Okay. If you have a 50% duty cycle, that means the pulse is high 50% of the time and then low 50% of the time. So 50% on, 50% off. That's a 50% duty cycle. You can increase that, right? So if you have 75% duty cycle, that means the pulse is actually high 75% of the time, 25% of the time is low. So notice that this doesn't change the frequency, right? These upswings, right, still lines up. So it's still the same frequency wave, but it determines how often the voltage is actually in its high mode versus low mode. Okay. You can reduce it to you can do a 25% duty cycle where your pulse is only high 25% of the time and then off 75% of the time. You can even do like a 1% duty cycle or a 99% duty cycle, right? So you can do a lot of extreme on that. Okay. And what it's going to allow us to do is do this technique called pulse width modulation. Notice that, these are the pulses, right? The width of this basically carries the digital information that you're going to be sending into your analog device, which is pretty neat. Okay. And the way this works is that the power output to a speaker, right? You can model that as a resistor. So the power is going to be the current times the voltage across that resistor or speaker, right? Equivalently, right? You can change that into just V squared over R, just using Ohm's law, right? This is used to transfer whatever analog information from a digital device, so you can have an analog output. So we can do I'm going to describe the simple pulse width modulation technique, and you can see how this allows you to basically send have like analog information be sent out by just having ones and zeros instead. Okay. So this is a picture. I don't know where I got this picture from. It looks pretty old, but this describes things very well. Okay. So let's say, right, this line in the middle here is the signal that you're trying to send, Okay. And then up here is a carrier sampling pulse, meaning that basically determines how often your wave gets sampled. Okay. So whenever there's a uptick, right, we're gonna sample. So the first sampling we're gonna do is here, right? So this is 0. Let's not set that at 0. Let's set this at 0. The bottom here, right? So you start off somewhere in the middle, and let's just call this 1, 2, 3, and then 4, right? So the wave never reaches quite 4. Okay. So if we sample here, right, it's like 2.6, 2.7. And what we do is then we pulse the width of the output on our pulse width modulation to be proportional to about 2.6 divided by, let's say, 5. Let's say the maximum output is 5. Okay. Okay. Actually, it's probably a little bit less than that. That's like about a third. Yeah. I think they're doing like a 6 as the maximum or something like that. Like 2.6 divided by 6. 2.6 divided by 6. Okay. All right. So that basically does the analog to digital conversion at this point here. The next uptick, right, we're going to do another sampling. Okay. And now the number is bigger, right? Now it's like about 3.5 or 3.6. Okay. So what happened there is that, well, now, right, since this is bigger than 2.6, we pulse it a little longer, right? Okay. All right. The next sampling, right, is around 3.6 again. So these should be pretty comparable to each other. So the pulse width modulation signal should be about the same. You can see that. Get rid of that. Right. When the wave gets smaller, the next sampling point over here, right? Once again, we're about 2.6 again, and then you get this here. Okay. Sorry, someone keeps calling me. Okay. Let's do another one where we can see that the pulse width are actually getting smaller. The next sampling point is over here. Right now it's like 1.2, so this will be pretty narrow. The next one is even narrower, right? So the amplitude of the wave that you're trying to convert from digital to analog, right? Depending on what that voltage is, right? The bigger the voltage, the longer you pulse that wave. But it does have to be, you cannot pulse it longer than the sampling rate, right? Because you're going into the next one, okay? So what you're doing is you're basically just dividing, right? Let's say this time is, let's say TS here, go away, right, is 10 milliseconds, right? So for a 2.6, maybe you're pulsing it, 2.6 milliseconds. So let's just make this to 10, just to make the math easier, right? But then when you go to 3, then you proportionally increase that fraction, right? When your analog signal is actually much larger. Okay, so you have this proportionality where the time that you spend having the pulse high is proportional to your the voltage that of the signal you're trying to emulate. Okay. I'm actually going to have you guys do that in the pre-lab. Basically complete this module using this template here, right? So you can have this is called simple pulse width modulation. I'll show you a little fancier one. Um, and you need a clock, right? Because the clock basically determines how often you're sampling. Okay, it's not necessarily 100 megahertz clock on the basses, right? It's whatever sampling rate you want. Okay, and you're gonna have an input, and this input basically is a 8-bit input, right? So if you're doing 8-bit, so you can the digital number can be 1 to 127. Okay, which is not in this case, but 127 max, right? And what you need to do is actually send this back as an output, and that's why it has to remember that. So that's why it's a registry, okay? And you start off by basically having a counter where you can count up from um, 0 to 127, okay? And this counter basically subdivides. So let me do a version of this here. Subdivide this period, right, into 128. So that's 128 division that you're doing on your pulse width modulation. And then when you're doing always at this um, positive edge of whatever that clock is, which is basically this, okay? What that does, actually, sorry, that's this clock has to be not the sampling, it's the sampling times, in this case, 128, okay? So let's say you're sampling at uh, 100 hertz. The clock in actually has to be 100 hertz times 128, okay? So 128, 12.8 kilohertz, okay? Sorry about that. I think that was misspoke on the previous part, okay? And what you want to do after this is that you want to make the pulse high for the number of clock cycles that whatever your xn is. So if your xn is 128, sorry, 127, you can't do 128 because it's 8-bit. So if your xn is 127, right, you want to make that high basically all the time, okay? But if your xn is 1, you only want that to be high just one of the clock cycle, okay? And I will let you write that. I think that's a little fun little exercise to do this simple pulse width modulation, okay? Let's see. What I'm going to show you how to do is do a slightly fancier version of it, which is known as sigma delta pulse width modulation, okay? So the way this works is that, well, you have this is your analog signal, even though it doesn't look like it. Okay. What you want to do is that whenever you have a low input, so let's say, you have, so let's say this is at 0 and this is the maximum number is 127, right? And this is probably like 60 or something like that, right? When this is low, you want to pulse that, but not as often. But when you have a high digital number that you're trying to convert to analog, you pulse it very often, okay? And this is known as sigma delta. Sigma is these width, and then delta is the distance between them, okay? And this is how you can do pulse width modulation using this pulse width modulation technique instead. And the reason I'm giving you this so you can have something in the lab that works. But I'm going to have you try to write the simple one yourself in the pre-lab and implement it yourself in the lab itself. Okay, but I'll show you how to do this one, so at least you have one working one. Okay, this is the same. The module is called sigma delta, just to make the name different. Right, you have the same input. You have your clock in, which is basically how often you can change your output of your pulse width modulation to be high or low. Okay, so this will be whatever your sampling rate is times the number of bits that you're going to be, sorry, times the 2 to the number of bits. I didn't do that in red. 2 to the number of bits, right? So if you're doing 8 bits, this will be, 128. So if you want to do a sampling rate of 8 kilohertz, right, then this will be times 128. So so that will be about a million hertz, or so about 1 megahertz. So you want that clock in to be about 1 megahertz, which you can do with the passes pretty easily, right? And then you're going to have a pulse width modulation output, Okay. In this case, I don't have it as a registry because I'm not going to be sending this directly back. I'm actually sending, I'm having it remember sigma instead. Okay. But let's see how this little module work. Okay. The first thing I create is a registry so that I can remember things of 9 bits, not 8 bits. Okay. There's an extra bit, and we're going to see why we need that extra bit. Okay. And you start that at 0. That's the when you instantiate it, you start at 0, but that number is going to change, right? So at every clock impulse, okay, what happened is that I'm going to change the first, the lowest 8-bit. Okay, you notice that this is ninth, this is the 9th bit. This is actually starting at 8th bit. Okay, what I'm going to do is I'm going to add whatever my input is into it, right? If the input is 0, then you're adding nothing to it. But if your input is 255, then you're adding a bunch, a large number to it. Okay. And that becomes my new sigma, which is the 9-bit sigma. So on the left-hand side here is 9-bit. On the right-hand side is actually 8-bit. So I'm adding stuff, but I'm not adding the 9th bit, the most significant bit. Okay. And then what I'm doing is I'm assigning whatever the pulse width modulation output to be the 9th bit. Okay, so how does this work? So let's just do some quick example here and how this works. Okay, so on this little table, I have the clock cycles. Okay, so let's say I'm going to start off the sigma variable to be 0. Okay, I'm going to write this in decimals just so it's easier to understand, right? If my input is 255, right, the next cycle that I'm going to add to it, I'm going to add 255, right? So therefore, right, the 9-bit version of it, right? So the 8-bit binary representation for 256 is 11111 with 8 ones, right? But remember that we're not modifying the 9th bit there. Okay, so that does nothing to the 9th bit. So therefore, right, the pulse width modulation output is still 0. Nothing happening there. Okay, but what happened is that the next time it pulses in, the next pulse, right, what happened is that, well, I started off at 255, I added another 255 to it, so now the decimal value of my entire 9-bit sigma is 510 now. Okay, if I convert that to binary, I get 1 and then a bunch of zeros, and then you get the last you get a bunch of ones, and then the least significant bit is 0 because it's not 511, it's 510. Okay, so in this case, right, the 9th bit went from 0 to 1. Okay, so that pulses the pulse width modulation to be high at the first point. Okay, but then, well, X is still 255, so the next clock cycle that goes in, I get another 255. Okay, but instead of the decimal number being 510, right, I overlap to the next, I basically go cycle it through. I overwrite this binary number. What happened is that value becomes 509 instead. Okay, basically this little bit gets shifted up one at a time. Okay, well, but this number is still bigger than 255. Therefore, the most significant bit, the 9th bit, is still staying at 1. So this is going to stay at 1 for 200 for cycle 1 to cycle 255, meaning 254 of the cycles is going to pulse high. So therefore, in this case, you're going to get, right, so let's say this is the 1 cycle. Let me erase this. I'm going to do that in black. Okay, so this is kind of drawing, right? This is 1 sample cycle, right? 1 sample, right? And what happened is that the first cycle you're going to get 0, but then the rest you're going to get high. Okay. All right. Hopefully that helps. Let's do one more just so that we see that this works for other um, an, analog numbers, right? So let's say xn is 127 instead. Okay. Once again, we're going to start off with the thing being 0. Okay. In fact, I'm going to draw this at the same time, so it's a little bit easier. So this is one sample. Okay. Okay. The first time it goes in, right? You don't get you don't overshoot it to 255 over over um 256 or above. So therefore this number stays at 0. And then the second times what happened is that you add another 127 to it. 127 plus 127 is 254. You are still below 256, right? Therefore the pulse width modulation here stays low. Okay. But then next time you add 127 to it, right? You add this number, it pushes you over the 255 number, right? Now the pulse width modulation goes high. Okay. For one cycle. Okay. But right, this 0 bit here, when it wraps around, what happened is that when you add 127 to 351, since it's only a 9-bit number, you get an over shoot, and then it basically wraps back up to being to be 0, and then you add the 127 again. And what happened is that you go back down to 252. And so if you do the bits, what happened is that the most significant bit goes from 1 to 0, so you get 0, so you get low one cycle, and then this kind of keep going up and down, up and down, up and down, right? And this is basically approximately a 50% duty cycle, right? Where this is like 99% duty cycle, okay? So this pulse width modulation method allows you to basically change the duty cycle, not by having one long pulse, but a series of pulses that are spaced apart. And this is usually a little bit better for your both your computer system, for the digital system, and for your speaker, because you're not sending all of that power out all at once. You're kind of spreading it out throughout the entire cycle instead. So it's a little bit less wear and tear on the power output, let's say. Okay. One of the things to remember is that be a little careful about pushing these too low of a frequency, is that you may start hearing it if you push these down below 20 kilohertz. Okay, so that's all I'm going to cover. Oh, we're 43 minutes, so I will wrap up today, and then see you in the next lecture.